Now, the first thing I'd like to talk to you about is a perfect imaginary speaker and what that would actually look like. Now, you know what speakers look like. They have the membrane, and that membrane is connected via rubber carriers to a box. So I'm drawing a profile of a speaker, and it's connected to a box, speaker box. What does that box serve? As you see, this membrane moves back and forth, pushing the air towards you and pulling the air away from you, actually creating air pressure, which translates to sound that you hear. Now, that's the front of the membrane producing the sound that goes to you. But what about the back? The air that's pushed in the back, it's exactly the same thing, just in the opposite phase. So when the front moves forward, the back also pulls toward you, creating that same sound but in the opposite phase, which means it wouldn't be too much of effective sound because it would annihilate itself. We create a box around the speaker so that we don't hear this back movement, this back air pressure being created. Actually, it stays inside the box. What a perfect speaker would be, it would be a speaker in an endless wall. So imagine a wall without an end. So none of these actually as borders exist. So an endless speaker in space. And then to make it even more complicated, this membrane would have to be zero mass. So it would have to have the least mass possible. Of course, perfect would be zero, so no mass at all. And that would serve us so that when the coil and the magnet we talked about in the previous lessons, when that magnet would move this membrane, it would move instantly. So zero mass would allow it to move as fast as the magnetic energy pushes it away or pulls it inside. That zero mass is, of course, impossible for speaker productions. People use really light materials. Now, what else? Well, we would have to have this membrane really, really stiff. So it should not wobble, if you know what I mean. So once we move it outwards, the complete surface should move outwards at the same time without wobbling. It would make the sound front incorrect. Now, it means that it wouldn't represent that music accurately. So we need it super stiff, super light, so that the dynamic response of the speaker would be perfect. We need it in an endless wall so that we're not capturing this inside wave pressure in a box, but it's actually on the other side of an endless wall. Now, what's wrong with capturing this air pressure on the inside of a box? Well, it builds up inside of this box, the air pressure, which is disallowing the membrane to move freely. Imagine that, pressure building up in the box and pushing back on the membrane, not allowing the membrane to move as the magnet is pushing and pulling, as the magnet is trying to transfer musical, information to us through the membrane. Now we would have to sit in empty space, so there would be no walls. There will be, as you know from acoustics that we went through, so there will be no walls, no floors, nothing that would make the sound we are listening to bounce off of anything else. So we would listen only to the sound of the speaker coming from the box to us. No other reflections of the walls, no other reflections of the floor, of the ceiling. So we'd have none of that. Of course, that is impossible. What is possible sometimes is that you can see in studios, in professional studios, you see the mixing console, and then you see all of those speakers, built inside a wall. So they are built into a wall so that you can only see the front plate of the speaker coming, being flat with the wall surface. Now that also serves a purpose of the sound reproduction being better. Now, how can the sound reproduction be better for us? Well, we need the speaker to deliver a flat frequency response, flat spectral response, meaning that if you remember all those frequencies that people hear that we talked about from 20 hertz to 20,000 hertz, we would need the speaker to produce everything we send through it flat and equal, which is also not possible. There is always some discrepancy, and speakers are usually fine-tuned to produce musical content really well. But just one of the qualities we seek inside the studio monitor, inside the studio speaker, is to have a spectral response as flat as possible. Of course, there are going to be some deviations on this graph. Usually, they're going to tend to be as flat as possible. So as much bass, as much mids, as much highs, flat. If we play this many decibels of low frequencies and the same amount in decibels of high frequencies and in mid frequencies, we're going to get the same loudness out of that speaker. Usually, this is produced by playing a sine wave sweep, meaning that sine wave ups its frequency slowly, starting to be like faster and faster and faster and faster and faster. And that way, we can see if that sweep inside the spectral metering is flat, if it's going to produce a flat signal. We record that with a microphone, of course, a flat response microphone. Usually it's piezoelectric. And this is how we measure. Now, this measurement is usually being done in the factory where speakers are produced. But once we get those speakers into our room, of course, we can do that measuring again to see how our room is affecting the spectral response, because it also might add something onto it, but we talked about that in the acoustics section of the course. Now, what else do we need from a studio speaker or monitor? We need good dynamic response. And I talked to you about this in the beginning of this very lesson. It's that the speaker moves very quickly with the magnetic force being pushed through it. So once we apply a magnetic force to push the speaker with the magnet and the coil, if you remember from the first lesson in digital analog audio, this speaker should move instantly. Of course, that's not possible. It has mass, has some mass, and that mass causes inertia. So when we push it, it struggles a little bit. We have gravity on this planet. So it's never going to be perfect, but they are made from really light materials. In the past, it used to be strengthened cardboard. Now, today, let's say my Atom speakers are made out of Kevlar. So it's really stiff and really low mass, so that when you push it, it moves as fast as possible, following the magnetic energy, and it's really light, so that it could move as fast as possible without wobbling, without changing its shape. Now, what other qualities do we have in speakers? Well, today you know that most of studio monitors and hi-fi speakers that we listen to music on to in our living rooms, and computer speakers too, are made out of more than one membrane, more than one speaker driver component. And that usually consists of maybe 2 or 3. That's why we call them a two-way system, a three-way system. So we have one membrane that produces low frequencies and one that produces high frequencies. So we have 2 speaker drivers in our speaker, one producing high frequencies, one producing the low ones. How is that achieved? Well, if you look again at the spectrum that we all hear, from 20 hertz to 20,000 hertz or 20 kilohertz, one of the speakers is producing one piece of the spectrum and the other speaker is producing the other piece of the spectrum, having this crossover here. So each one of those comes into the territory of the other one. But the manufacturer tries to keep this crossover point so fine that in the end we get a flat response. Of course, there is a question of phase too. So these need to be in phase. Crossover frequencies, they need to be in phase so that we don't have any distortion of sound. And I mean distortion in sense of phase cancellation. But this is all done in the factory. Now, in the end, we get a speaker from 2 or 3 drivers producing a flat spectral response for us, with the crossover frequencies carefully crafted and managed. Now let's talk about all of these different types of drivers that push different frequencies out of our speaker. So the high frequency ones, we have them in many different forms. They used to be drivers just like the ones, like membrane speakers, just like the low frequency ones, like the woofers, on the old types of hi-fi speakers. Now today we make those out of many different types of drivers. Usually it's dome, and these dome drivers are mainly constructed out of really light and really stiff material. They're usually made out of some metal alloy, titanium, beryllium, aluminum, anything that's stiff and really, really light. So they can produce this really thin membranes. And usually they don't look like this. They just look like a membrane, like this, just a dome. And if you have any kind of speakers at home, like studio monitor speakers at home, you can check if it's a membrane. You will see actually a metallic dome in it, or a dome made out of textile. It's usually made out of some sort of paper or silk textile, but it's coated fabric. It's always coated in something so that it stays, of course, stiff. Now we have those, and usually tweeter speakers, the higher the frequency produced is more directional. What does that mean? Meaning that out of that speaker that you see out of the front, the angle of producing sound, so if we look at that speaker from up above, I'm going to draw that from up above. Let's say this is the speaker right there, and this is another one right there. This is where it's pointing, the high frequencies. This is how much they cover of space. So not really a lot of the sound being produced around them, more in front of them, really. So if you sit anywhere aside of that speaker's path, you're not going to hear a really natural reproduction of sound. This is why speaker placement is really important, and we will be talking about that soon. If we talk about the bass producing membranes, these frequencies tend to spread a lot around the speaker, everywhere around the speaker. So if you look at that speaker from up above, it would go much more to the sides, even to the back of the speaker. Any frequency below 300 hertz, 200 hertz spreads everywhere. Why? That's the nature of air, the physics of air pressure being distributed through space. Basically, we have the high frequencies directional and low frequencies really non-directional, meaning that the low frequencies, for those, the speaker can be anywhere. And that's where we get to the subwoofer. You all know today the subwoofers, the big speaker that stands on the ground below your feet and produces just the lowest frequencies, let's say below 100 hertz, below 80 hertz. And it's down at your feet, but you can still hear it and feel it because those frequencies are really non-directional. So they travel everywhere around the speaker omnidirectionally. Now, why these are so big, if you've ever seen a membrane on a subwoofer, it's usually bigger than the membranes on your speakers that produce middle frequencies or high frequencies. Well, that has to do with physics. To produce a really low frequency push and to produce an air pressure in a low frequency, you need a bigger membrane. And that can also be calculated mathematically. So in order to produce a frequency as low as, 30 hertz, you need a membrane of a certain size. Otherwise, it's impossible. So having that said, let's talk about speaker positioning. Now that we know that high frequency speakers are usually really directional, low frequencies not so much, they are really omnidirectional. Let's talk about that. Positioning of the speakers in a studio, and let's take a look from the studio from up above, like that. The positioning rule also includes the listener. If we had these two speakers like that, right there, producing sound. Now we need this distance between the speakers to be the same distance to the listener. Let's say your head is right there with your ears listening. So we need this to be the same distance. So you are forming an equilateral triangle between you and the two speakers you have. Having that said, the height of your speakers should be such that the tweeter, if you know what I'm talking about, the tweeter, the high frequency producing one, this one, should be in the level of your ears, because those are really directional. So in order to hear them properly, those should be pointed directly at your ears. So they should be in your eye level once you're sitting down normally and listening to the sound produced by your studio. So we need these to be in the height of our ears. These don't have to be. Those are quite non-directional, so we have a way more tolerance when looking at the positioning of the low frequency speakers. But the sub would go somewhere on the ground, usually in the middle of these, and at a distance from you, that when this sound from this low speaker comes to you, the sub sound comes to you at the same phase. Thinking like that. And the sub should also come to you at the same phase. So we don't want any phase cancellation there either. That's also done by moving those speakers physically within the room until we get a good result. But this rule of forming an equilateral triangle between you and the speakers is really good. Now also we have the rule of how far the speakers should be from the wall and how far they should be from the sidewalls too. So you should always place them at the same distance from the walls. So as far as this speaker is from that wall, that should be the same distance. So that's B, and the C should also be the same. Why? Because it's gonna create a more unilateral sound front, which is not affected by the room as much, which is not being skewed by the room as much. Okay, you all seen speakers on speaker stands. And why? Well, imagine one big board and you have both of your speakers on that board playing towards you. Now, this speaker moving, producing sound, it shakes, it moves, it trembles, and it will move this mechanical board it stands on, and in turn, that board will move this speaker, moving this speaker, and then this one would move that one. So they are affecting each other in a mechanical way. What we need the speaker to do is be really stiff so that it doesn't move. It's the membrane that moves. We want the box to be really static. Now, the box is not static if it's being shaken by the vibrations of the other speaker. So this mechanical connection is not really good. What we need these speakers to do is to be mechanically separated. That is why we have speaker stands, so that each speaker is on top of its own stand, avoiding the contact between them as much as possible. Avoiding mechanical contact between them as much as possible, because this is how vibration is being spread around. And usually these speaker stands are placed on really narrow spikes. And you might have seen that too, but why on spikes? Well, mechanical energy is transferred through the surface of mechanical touch. So the narrower the touch surface is to the ground, the less of that energy from the speaker shaking is going to be transferred to the floor, and then that energy again transferred to the other speaker, of course. That is also going to help with your neighbors not hearing that much of that floor shaking that your speakers are inducing into the floor. So that all is kind of physics interplay between them. This is why we need mechanical separation, meaning we need the speakers not to affect one another with their vibrations. Now, we already talked about directiveness of certain frequencies when talking about tweeters, woofers, subs, but let's talk about headphones. Once you've seen all of this, you might just wonder, well, why don't we just use headphones? We don't have any of those problems. And none of that speaker positioning, none of the room acoustics and room absorption, treatment. And doesn't that sound more logical, more less expensive, of course, cheaper to maintain? Now, headphones, for some reasons, of course, when I'm doing my mixes, I would check them on various amount of speakers and also headphones, of course, in the car and in really tiny headphones on a mobile device. But that's a different issue, checking the mix. Now, when talking about headphones, one thing you can certainly differentiate between headphones and speakers is that while listening to headphones, each one, let's say this is your head. My drawings are so bad. Okay, I like this now. That's gonna be cool. Okay, now you have these headphones. When you look at this, now you see that each one of your ears is listening only to the left or the right channel. So this is the left one, this is the right one. Now, the right ear can hear only the right channel, only the right speaker, and the left ear can only hear the left speaker. This is not the case with speakers, with normal studio monitors. When you're listening to the studio monitors, let me delete this. When you're listening to the studio monitors, both of your ears can hear both of these. So here you get a stereo image, of course, because they are separated. You get a stereo image nicely, and the depth coming from reverberation you introduced into your mixes, but it's a different kind of a soundstage. You do hear each one of these speakers with both ears. And when listening with headphones, you don't have that. So that's where the difference lies. Of course, think about the frequency response. Now, how big would the headphones have to be to produce a really, really low frequency? As we talked about before, the size of the membrane is actually physically connected to the lowest frequency it can produce. So the bigger the membrane, the lower the frequency it can produce. Why would we need a subwoofer that big if a small headphone like that can produce the same frequency and give us the same effect? That would not be possible. So there are things that are really good to hear on headphones, like some minor details, clicks, pops, noises, a different sound stage, and 3D separation in your reverbs, and the space of your song is going to sound different in the headphones. And of course, it should sound good on the headphones and on the speakers. But there is a difference, and there is a reason why we use speakers, because mainly we need the song to be nice when reproduced with the speakers. Now, what does that entitle? Well, if we have a speaker here, and we have the listener in the middle, well, that doesn't look so good. It's like a character out of South Park. But if we have a low frequency coming from this speaker, like that, and we have a low frequency coming from that speaker like this, and they are in opposite phases, if you sit exactly in the middle between these speakers, there is going to be no bass. It's going to cancel itself out. So now I'm going to play you an example. I'm just going to use a song, and I'm going to create this effect for you. And you can test it out and see that when you're listening to that song on headphones, you don't have that bass canceling effect. But if you listen to it on the speakers and you actually place your head exactly between two speakers, exactly the same distance as I've shown you, you will see that the bass actually disappears. And if you move yourself to one side or the other side, the bass appears magically. So that's one of the things to take into consideration. And I'll play the example for you now. Now, what I can do as an example is I have the synthesizer and I made a bass sound out of sine waves, but it's completely stereo. So it's completely the opposite phase in both of these. So it's the most stereo it can be. And I'm going to show you why that is bad. Now, if you're listening through the speakers, you can probably get this first part of the example right. If you just try to position yourself at the equal distance from both speakers, as I've shown you in the example before, as how you should be positioned in your studio, you can hear that once I play this and you're in the equal distance from them, Then if you move closer to one of them, the bass becomes louder because it's not canceling itself that much. So I'm going to play it, and you can stand in the middle and then just go closer to one of those, to one of your speakers. So be in the middle and then go closer to one of the speakers. Let's try that. Now, even so, when you have an example like this, where if you're in the club where they do have a stereo system and you're in the wrong spot because the bass is stereo and it's canceling itself out that much, and it's actually quieter in this piece of like in this space in the club, it's quieter than anywhere else, which is of course bad. But most of the clubs, because they have various rooms and various speaker positions, have a monoed out system, meaning that they play both left and right channels on all of the speakers. So they are monoed out. So what would happen if I actually made this bass mono? I did the same thing they do in the club. So I put the width at 0, and now I'm actually playing both left and right on both of the channels. We're going to get nothing. I'm going to play a note. And if you can see, there is no sound. So the sound is coming in from Serum, from the synthesizer. The sound is coming in. But once those two signals are added, they are completely the opposite thing, and they produce zero sound. So this is what would happen if you had a club that had a signal monoed out. So they had a monoed out system where both left and right play on both speakers. You would get no bass. So doesn't mean that the bass has to be totally zeroed out like this. That would happen if the bass is completely stereo, so opposite phase, the most stereo it can be. Even if it was a little bit stereo, it would cancel itself out just a bit less. So let's do that. The more I change this phase, the less is going to be zeroed out. So we get the most volume when it's actually in the same phase for the left and the right speaker. Now let me show you what that signal looks like, actually, so you realize why it's converting into 0. Let me remove this. Make a note right here. Maybe a lower one, of course. Okay, now I'm going to freeze this so you can see the audio signature of that. Flatten. Okay, now you can see the audio. You see that they're completely opposite. So if you added two identical but opposite phase signals, you get 0. Simple as that. So if your bass frequencies are being stereo, they are going to cancel each other out, at least in some portion, and then your song balance of bass, mids, and highs is not going to be proper. It's not going to be the same on every sound system you play it on. Now, to demonstrate problems like this on a real world example, I'm going to play you this track, and at some point in time, I'm going to make the entire song mono, and thus you will hear what is being lost. So I have on purpose made this song with the bass that is completely stereo, and this is not a good thing, of course, but the subject of this example is to show you that maybe on the headphones you wouldn't be able to recognize this, while in the studio with the speakers you could recognize this by sitting in the middle. You would hear that something's being off, that the phase of the bass and certain elements in the song is off. And how we're going to actually show you this is I'm going to make the entire song mono. So the song is going to play us everything that's mono. I'm going to add left and right channels together and play them off of both speakers. Now, this is what would happen in most clubs. As you might have noticed, in clubs, there is a lot of speakers in different areas, different places, and there is not really a means to play you a stereo image, like a left speaker on your left side and a right speaker on your right side, because you could be standing anywhere in the club and you could be turned any direction in the club. So there is no way for them to make a sound system that's going to always have a left speaker on your left and a right speaker on your right side. So they would essentially always do this. So add left and right channels together and play them both off of all of the speakers in the club. Now, the problem with that is going to happen when you have something in your song that looks like this, like the bass in this track, like what I'm going to play you right now. Let me play you an example. Okay, now that's enough. Having your headphones on and listening to this, the bass sounds okay. There is bass in the track, you can hear it. Now, why I deliberately made it so stereo is that when I do this operation where everything is mono, you will hear that everything that was super stereo just disappears out of the image of the song. So I'm going to disable this plugin, play the track, and then I'm going to enable it halfway through, of course. As you can see, once I enable this, when the yellow light is on, almost everything, the entire bass information just disappears, since all of the frequencies of those instruments are actually opposite phases on the left and right channels. So when I add them together, they cancel each other out. This can happen with many of the instruments you play in your tracks, and we will get further into these phasing problems once we get into mixing, mastering, production. Also, you take care of these issues for as long as you're making the music and producing it and mixing it at every step of the way. So this example particularly is to show you what would happen to a badly written track which has elements that are so much stereo that in the club, when reduced to mono, this track loses some of its elements. Now, why is this important? This is a part of, in the software we're talking about hardware, but we're talking about hardware because on the headphones it will be harder to recognize something like this, and on speakers you might notice the cancellation and the disappearance of certain elements because you're sitting front and center between your speakers